Okay.
If I went up to anyone here and asked them, what are you made of? I can be assured I would get a radically different answer depending on who I asked. Some bright and cheery 7 might say something boring like my hopes and dreams. A year 9 would probably ignore me and mutter something under their breath, knowing year 9s. A GCSE student might try and wow me with their knowledge of the human anatomy. Sorry, I don't care. A 6th former would most definitely say despair, misery, or something to that effect. And any member of the teaching body would be obliged to state that PHS girls are made of grit and determination. However much they believe this to be absolute truth, I feel like I might have to let them down gently by saying there is a bit more to it than that. So let's just take the human body. If we zoomed in on ourselves, took slices at various layers, placed them on a petri dish and looked at them through a microscope, what would we see? We are made up of cells. Skin cells, red blood cells, white blood cells, muscle cells, nerve cells, and many more. Cells are the basic building blocks of life, is something that I'm sure you've heard many times. And it's true in some respects. All multicellular life forms are made out of, well, cells, working together to fulfill various functions. We know that cells can be broken down too, into mitochondria, cytoplasm, nucleus, and inside that, DNA. DNA codes for a combination of amino acids that codes our genetics, forming the basis of us. It's what makes you, you, and me, me. So we could say that all we are meat sacks identified by strings of amino acids. Nice. If you could zoom in even closer, you would find individual atoms of each element. Now, if in biology you learn that cells are the basic building blocks of life, then in chemistry you learn that atoms make up everything. The word atomos is Greek for indivisible, which is how they were described by 300 BC philosopher Democritus. The simple model of an atom, as we understand now, was discovered by Rutherford firing alpha particles at a Gulf War screen. So our current basic understanding is a tiny dense nucleus of protons and neutrons being orbited by even smaller electrons. So even now we can see that an atom isn't actually atomos, indivisible, it's made of these 3 fundamental particles. Fair? Well, yet again, this isn't entirely accurate. Now, this model of an atom held for a fair while, but in 1964, 2 guys, Murray Gell-Mann and George Zweig, both independently came up with this thing called the quark model, using a lot of complicated maths and funny equations and things like that. So now, yet again, we have another fundamental, definitive model of the atom, where particles like protons and neutrons are made up of quarks. You can see here. So has this ever been seen? We have some pretty famous places where experiments on this can actually be performed. The most well-known place is CERN in Geneva, which has a particle accelerator, a massive tunnel in which particles, usually protons, are accelerated round to near the speeds of light and then smashed together. Detectors are used to see all the fragments that fly off them. So if protons are made of quarks, then we should see quarks flying off, right? Well, there's a bit of a problem with that. See, quarks have never been observed alone due to something called quark confinement, which makes it a bit of an issue to actually see quarks. But what we do see are particles which are also made of quarks, things called mesons, which are made of 2 quarks, rather than the 3 which make up things like protons and neutrons. So whilst we can mathematically prove the existence of quarks, and it can be inferred from different interactions of particles, we've never actually seen any. Helpful. So from our 3 fundamental constituents of the atom, we've just learned that protons and neutrons aren't fundamental, but are actually made up of quarks. So what's left? Electrons. Now I have got some good news. Electrons are actually fundamental. Yeah, there is nothing more to it than that. Electrons are just small, dense little particles. Except they can also be seen as waves of energy. Yes, in 1905, Einstein published 4 very important papers. One of them detailing a process called the Photoelectric Effect, in which he very hesitantly suggested that light was not a wave, but actually a particle. The uneasy truce made between the 2 warring sides of this debate is that light has the potential to act in wave ways and particle ways. It has wave-particle duality. It isn't one or the other, but both. And then in 1924, this chap Louis de Broglie had the slightly nauseating hypothesis that if waves can act as matter, then matter can act as waves. So not only does light show wave-particle duality, but so does all matter, including electrons. One property of light that I'm sure you could remember if you tried hard enough is that when it goes through a small gap or round a corner, it diffracts. And if you fire a stream of electrons through a small gap, somehow it diffracts too. So you can see the diffraction pattern here, which is similar to the pattern you would see if you shone light through this gap. And so de Broglie came up with an equation which is lambda equals h over mv. So the de Broglie wavelength of matter is equal to Planck's constant, just a really small number a bloke called Max Planck came up with in the 1800s, over the mass multiplied by the speed of the particle. So if all matter can behave like waves, then so can quarks. So can every bit of matter, every fundamental particle, and everything around us. So you can see that electrons can behave like normal waves or particles, but what would you actually see if you zoomed in on an electron, down to the ultra small, and see what no one has seen before? Would you see the particle, a spherical blob, or a wave, whatever a wave looks like? Well, unfortunately, you would see neither, because this is when particles get even more complicated. Werner Heisenberg in 1927 made a massive contribution to quantum mechanics called the uncertainty principle. This states that the more precisely the position of a particle is known, the less precisely its momentum is known, where momentum is just mass times velocity, so it's usually just shortened to speed because the mass remains constant. A particle, like an electron, is just so vague. Where it is, what speed it's travelling at, even what form it's in, are kind of fuzzy to us. We know roughly, but we can't know all of this exactly at the same time. We can't just point to a blob and go, there's an electron at XYZ coordinate travelling at v meters per second. Now, this is quite an interesting rule, which is related to, and often confused with, the observer effect in physics. So the observer effect means the thing you're observing could be anywhere, anything, at any speed until you measure it. So just think of a phone, made in a factory without any humans, constructed purely by machines. The phone is made and put into one box by the machines and sealed. But the machines are faulty. For every one box with a phone in it, there are 9 boxes without phones. You and 9 friends, then perhaps foolishly, decide to buy phones from this company. We will say for the sake of this, there is guaranteed 1 phone in each 10 boxes, and we will also assume that you have 9 friends. Only when you unwrap them all can you actually tell which box has the phone in it. You don't know which box has the phone in it beforehand, and no human in the world does. It was made only by machines. So only when you unwrap them can you tell that one friend, say box number 3, has the phone in it, but the rest of you just wasted your money. Now, the phone was always in box number 3, but until you opened the boxes, you didn't know this. Each box had the probability of 1 in 10, 0.1, of having the phone in it. The same can be said of a particle travelling in space. Until you look at it, directly measure where it is, it could be anywhere. Not only do we say it can be anywhere, we actually say that it is everywhere. So a bit like the Schrodinger's cat paradox, which was actually a thought experiment made to demonstrate to people the observer effect. The cat is both dead and alive until we look at it. The particle is everywhere in the room until we detect it. We show the probability of the particle being anywhere at one time as a particle's wave function. When we observe the particle and rule out where it cannot be, showing exactly where it is, we say the wave function collapses. Instantaneously, the probability of the particle being anywhere in the room rather than where it is becomes 0 because we know it's not there, and the probability of it being where it is becomes 1. There is no more uncertainty to its position. So you can see with the phones, the probability, that would be a probability distribution, that would be kind of like the wave function, and then immediately when you detect where it is, the wave function collapses because you know exactly where it is, and you know that it cannot actually be anywhere else. So, however, linking this back to the uncertainty principle, if we now know its position very accurately, we then know its speed very inaccurately. So this is a rather repetitive, unhelpful cycle. In this respect, answering the question, what are we made from, we would answer a wave function. We are simply a diagram showing the probability that we are in at any one place. Or, referring to the uncertainty principle, we know what we are, sort of, but not where exactly. We're uncertain. So yet again, very helpful answers. Okay, so if you're sitting there with your brain a bit melted, don't feel bad. Just know this is how I feel constantly, perhaps explaining my not always bright and shiny mood. So just to end, I wanted to look at something that people might actually have heard of before, string theory. Now, everything else so far has been more or less truth, with substantial evidence behind it, and a solid foundation of belief for several years. But this next thing is conjecture. It's bizarre, it's confusing, it's not necessarily true, which is what I tell myself in order to not have a mental breakdown. This is string theory. Okay, so string theory is one of the contenders for a theory of everything. So a theory to unify quantum mechanics, so most of the stuff I've talked about today, and the mysterious force of gravity. This theory states that every fundamental particle, so all quarks and leptons, where a lepton is just a category of fundamental particle that things like electrons fall under, are just manifestations of the same thing, a vibrating string. Yeah, this particle suggests that if you zoom in on, say, an electron, it's a particle, it's a particle, it's a particle, and then it's a loop of one-dimensional string. To be quite fair, thinking of anything in one dimension is upsetting enough for me. But entwining that with particles, which work in at least 4 dimensions, and string theory suggests it works in up to 11 dimensions, is something else entirely. So an electron may be a loop vibrating in one directional way, but if that way is slightly changed, then you now have a quark, or a bit of light, a photon. They're all made of the same fundamental stuff. So if we take this as gospel, we are composed of oscillating strings acting in bizarre ways. So looking at this poorly edited diagram summary here, you can see that there are so many ways to interpret this question, what are we made of? It almost seems like a stupid question to ask. All we know is that the atoms in our body are those that were around billions of years ago in the Big Bang. They may interact mysteriously with other particles on the other side of the galaxy through odd concepts such as quantum entanglement, but then again, they might not. We don't know enough about it. We don't even really know what they are. We are just the residue, the dust left over from the formation of the universe, come together in a supposedly intelligent being. It's funny to think that, in the end, we are made of dust, of dirt. You could even say, fundamentally, that PHS girls are made of grit. Thank you for listening.